Ernst Karl Abbe was a German physicist, optical scientist, entrepreneur, and social reformer. Together with Otto, Schott, and Carl Zeiss, he laid the foundation of modern optics. Abbe developed numerous optical instruments. He was a co-owner of Carl Zeiss AG, a German manufacturer of research microscopes, astronomical telescopes, planetariums, and other optical systems. Personal life. Abbe was born the 23rd of January 1840 in Eisenach, Saxe-Weimar Eisenach, to Georg Adam Abbe and Elisabeth Christina Bachfeldert. He came from a humble home. His father was a foreman in a spinnery. Supported by his father's employer, Abbe was able to attend secondary school and to obtain the general qualification for university entrance with fairly good grades at the Eisenach Gymnasium, which he graduated from in 1857. By the time he left school, his scientific talent and his strong will had already become obvious. Thus, in spite of the family's strained financial situation, his father decided to support Abbe's studies at the universities of Jena and Göttingen. During his time as a student, Abbe gave private lessons to improve his income. His father's employer continued to fund him. Abbe was awarded his Ph.D. in Göttingen on the 23rd of March 1861. While at school, he was influenced by Bernhard Riemann and Wilhelm Eduard Weber, who also happened to be one of the Göttingen Seven. This was followed by 2 short assignments at the Göttingen Observatory and at Physikalische Verein in Frankfurt. On 8 August 1863, he qualified as a university lecturer at the University of Jena. In 1870, he accepted a contract as an associate professor of experimental physics, mechanics and mathematics in Jena. In 1871, he married Else Snell, daughter of the mathematician and physicist Carl Snell, one of Abbe's teachers, with whom he had 2 daughters. He attained full professor status by 1879. He became director of the Jena Astronomical and Meteorological Observatory in 1878. In 1889, he became a member of the Bavarian Academy of Sciences and Humanities. He also was a member of the Saxon Academy of Sciences. He was relieved of his teaching duties at the University of Jena in 1891. Abbe died the 14th of January 1905 in Jena. He was an atheist. Life work. In 1866, he became a research director at the Zeiss Optical Works, and in 1868 he invented the apochromatic lens, a microscope lens which eliminates both the primary and secondary color distortion. By 1870, Abbe invented the Abbe condenser, used for microscope illumination. In 1871, he designed the first refractometer, which he described in a booklet published in 1874. He developed the laws of image of non-luminous objects by 1872. Zeiss Optical Works began selling his improved microscopes in 1872. By 1877 they were selling microscopes with homogeneous immersion objective, and in 1886 his apochromatic objective microscopes were being sold. He created the Abbe number, a measure of any transparent material's variation of refractive index with wavelength, and Abbe's criterion, which tests the hypothesis that a systematic trend exists in a set of observations. Already a professor in Jena, he was hired by Carl Zeiss to improve the manufacturing process of optical instruments, which back then was largely based on trial and error. Abbe was the first to define the term numerical aperture as the sine of the half-angle multiplied by the refractive index of the medium filling the space between the cover glass and front lens. Abbe is credited by many for discovering the resolution limit of the microscope, and the formula, although in a publication in 1874 by Helmholtz. Helmholtz states this formula was first derived by Joseph Louis Lagrange, who had died 61 years prior. Helmholtz was so impressed as to offer a professorship at the University of Berlin, which he refused due to his ties to Zeiss. Abbe was in the camp of the wide aperturists, arguing that microscopic resolution is ultimately limited by the aperture of the optics, but also argued that depending on application there are other parameters that should be weighted over the aperture in the design of objectives. In Abbe's 1874 paper, titled A Contribution to the Theory of the Microscope and the Nature of Microscopic Vision, Abbe states that the resolution of a microscope is inversely dependent on its aperture, but without proposing a formula for the resolution limit of a microscope. In 1876, Abbe was offered a partnership by Zeiss and began to share in the considerable profits. Although the first theoretical derivations of EQ1 were published by others, it is fair to say that Abbe was the first to reach this conclusion experimentally. In 1878, he built the first homogeneous immersion system for the microscope. The objectives that the Abbe-Zeiss collaboration were producing were of ideal ray geometry, allowing Abbe to find that the aperture sets the upper limit of microscopic resolution, not the curvature and placement of the lenses. Abbe's first publication of EQ1 occurred in 1882. In this publication, Abbe states that both his theoretical and experimental investigations confirmed EQ1. Abbe's contemporary Henry Edward Fripp, English translator of Abbe's and Helmholtz's papers, puts their contributions on equal footing. He also perfected the interference method by Fizeau in 1884. Abbe, Zeiss's son, Roderick Zeiss, and Otto Schott formed, in 1884, Jena Glass Work Schott and Amp, Jenison. This company, which in time would in essence merge with Zeiss Optical Works, was responsible for research and production of 44 initial types of optical glass. Working with telescopes, he built image reversal system in 1895. In order to produce high-quality objectives, Abbe made significant contributions to the diagnosis and correction of optical aberrations, both spherical aberration and coma aberration, which is required for an objective to reach the resolution limit of EQ1. In addition to spherical aberration, Abbe discovered that the rays in optical systems must have constant angular magnification over their angular distribution to produce a diffraction, limited spot, a principle known as the Abbe sign condition. So monumental and advanced were Abbe's calculations and achievements that Fritz Zernike based his phase contrast work that he was awarded the Nobel Prize in 1953, and Hans Busch used them to work on the development of the electron microscope. During his association with Carl Zeiss's microscope works, not only was he at the forefront of the field of optics but also labor reform, as he also, in 1900, introduced the 8-hour workday in remembrance of the 14-hour workday of his own father. In addition, he created a pension fund and a discharge compensation fund. In 1889, Ernst Abbe set up and endowed the Carl Zeiss Foundation for Research in Science. The aim of the foundation was to secure the economic, scientific, and technological future, and in this way to improve the job security of their employees. Quote, he made it a point that the success of an employee was based solely on their ability and performance, not on their origin, religion, or political views. In 1896, he reorganized the Zeiss Optical Works into a cooperative with profit sharing. His social views were so respected as to be used by the Prussian state as a model and idealized by Alfred Weber in the 1947 book Schriften der Heidelberger Aktionsgruppe zur Demokratie und zum freien Sozialismus. The crater Abbe on the Moon was named in his honor. Bibliography. Abbe was a pioneer in optics, lens design, and microscopy, and an authority of his time. He left us with numerous publications of his findings, inventions, and discoveries. Below is a list of publications he authored, including many links to the scanned Google Books pages. Abbe, Ernst, über einen neuen Beleuchtungsapparaten Mikroskop. Archiv für mikroskopische Anatomie. Bonn, Germany, Verlag von Max Cohen and Amp, Sohn, 9-469-480. DO 10.1007, BF 029566177. Betrachtung zur Theorie des Mikroskops und der mikroskopischen Wahrnehmung. Archiv für mikroskopische Anatomie. Bonn, Germany, Verlag von Max Cohen and Amp, Sohn, 9-413-468. DOI 10.1007, BF 029566173. ISSN 0176-7364. Retrieved 27 August 2010. Neue Apparat zur Bestimmung des Brechungs unserer Strömungsvermögens und flüssiger Körper. Genetische Zeitschrift für Naturwissenschaft. Jena, Germany, Mux Verlag 8-96-174. A new illuminating apparatus for the microscope. The Monthly Microscopical Journal. London, UK. Robert Hardwick. 1377-82. DOI 10.1111J 1365-2818.1875 TB00845X. Lawson, Henry ed. Translated by Fripp H. E. A contribution to the theory of the microscope and the nature of microscopic vision. Proceedings of the Bristol Naturalists Society, London, UK. Williams and Amp, Northgate, 1-200-261. Ed. Extracts from Dr. H. E. Fripp's translation of Professor Abbe's paper on the microscope. The Monthly Microscopical Journal. London, UK. Williams and Amp, Northgate, 14-191-201. Ed. Extracts from Dr. H. E. Fripp's translation of Professor Abbe's paper on the microscope. The Monthly Microscopical Journal. London, UK. Williams and Amp, Northgate, 14-245-254. Über mikrometrische Messung mittels optischer Bilder. Genetische Zeitschrift für Naturwissenschaft. Jena, Germany, Verlag von Gustav Fischer, 11-17. Über Blutkörpererlangung. Genetische Zeitschrift für Naturwissenschaft. Jena, Germany, Verlag von Gustav Fischer, 98-105. Über die Bedingungen des Aplanatismus der Linsensystem. Genetische Zeitschrift für Naturwissenschaft. Jena, Germany, Verlag von Gustav Fischer, 129-142. Über die Grenzen der geometrischen Optik. Genetische Zeitschrift für Naturwissenschaft. Jena, Germany, Verlag von Gustav Fischer, 71-109. Crisp, Frank ed. On Stevenson's System of Homogeneous Immersion for Microscope Objectives. Journal of the Royal Microscopical Society. London, UK. Williams and Amp, Norgate. 2-256-265. DOI 10.1111 J 1365-2818.1879 TBO 1651 X ed. On new methods for improving spherical correction applied to the construction of wide-angled object glasses. Journal of the Royal Microscopical Society. London, UK. Williams and Amp, Norgate. 812-824. DOI 10.1111 J 1365-2818.1879 TBO 1548 X. Über die Bestimmung von Zeiten Polhohe Ausbeobachtungen in hohen Parallelen. Genetische Zeitschrift für Naturwissenschaft. Jena, Germany. Verlag von Gustav Fischer. 57-66. Über die Bestimmung der Brechungsverhältnis fester Körper mittels des Refraktometers. Genetische Zeitschrift für Naturwissenschaft. Jena, Germany. Verlag von Gustav Fischer. 35-44. Crisp, Frank ed. Conditions on Aplanatism of Systems of Lenses. Journal of the Royal Microscopical Society. London, UK. Williams and Amp, Norgate. 3-509-515. ed. Some Remarks on the Apatometer. Journal of the Royal Microscopical Society. London, UK. Williams and Amp, Norgate. 320-31. DOI 10.1111 J 1365-2818.1880 TBO 5648 X. ed. Conditions of Aplanatism for Wide-Angled Pencils. Journal of the Royal Microscopical Society. 2. London, UK. Williams and Amp, Norgate. 1-831. ed. The Essence of Homogeneous Immersion. Journal of the Royal Microscopical Society. 2. London, UK. Williams and Amp, Norgate. 1-526. ed. Illumination for Binocular Microscopes with High Powers. Journal of the Royal Microscopical Society. 2. London, UK. Williams and Amp, Norgate. 1-690-692. ed. Penetrating Power of Objectives. Journal of the Royal Microscopical Society. 2. London, UK. Williams and Amp, Norgate. 1-831-832. Beschreibung eines neuen stereoskopischen Oculars. Reproduktion für Experimental Physik für Physikalische Technik. Munich, Germany. Druck und Verlag von A. Oldenburg. 17-197-224, ed. Origin of Homogeneous Immersion. Journal of the Royal Microscopical Society. 2. London, UK. Williams and Amp, Norgate. 1-131-134, ed. Conditions of Microstereoscopic Vision Penetration. 2. 1. London, UK. Williams and Amp, Norgate. 680-689. ed. On the Estimation of Aperture in the Microscope. Journal of the Royal Microscopical Society. London, UK. Williams and Amp, Norgate. 1-388-423. DOI 10.1111 J 1365-2818.1881 TBO 5909 X. ed. On the Conditions of Orthoscopic and Pseudoscopic Effects in the Binocular Microscope. Journal of the Royal Microscopical Society. 2. London, UK. Williams and Amp, Norgate. 1-203-211. DOI 10.1111 J 1365-2818.1881 TBO 5902X. Ed. Abbe Stereoscopic Eyepiece. Journal of the Royal Microscopical Society. 2. London, UK. Williams and Amp. Norgate. 1-298-299. Ed. Miniatured Images. Journal of the Royal Microscopical Society. 2. London, UK. Williams and Amp. Norgate. 2-693-696. Ed. The Relation of Aperture and Power in the Microscope. Journal of the Royal Microscopical Society. London, UK. Williams and Amp. Norgate. 2, 300-309. DOI 10.1111 J 1365-2818.1882 TBO 0190X. Ed. The Relation of Aperture and Power in the Microscope. Journal of the Royal Microscopical Society. 2. London, UK. Williams and Amp. Norgate. 2, 460-473. DOI 10.1111 J 1365-2818.1882 TBO 4805X. Ed. The Relation of Aperture and Power in the Microscope. Journal of the Royal Microscopical Society. 2. London, UK. Williams and Amp. Norgate. 3, 790-812. DOI 10.1111 J 1365-2818.1883 TBO 5956X. Ed. Note on the proper definition of the amplifying power of a lens system. Journal of the Royal Microscopical Society. London, UK. Williams and Amp. Norgate. 4, 348-351. DOI 10.1111 J 1365-2818.1884 TBO 1110X. Ed. On the Mode of Vision with Objectives of Wide Aperture. Journal of the Royal Microscopical Society. London, UK. Williams and Amp. Norgate. 420-27. DOI 10.1111 J 1365-2818.1884 TBO 2005X. The New Microscope. S. Jena Gs med 2-107-108. Überverbersierungen des Mikroskop mit Hilfe neuer Arten optischen Gläses. Messapparat für Physiker. Zeitschrift für Instrumentenkunde. 10-446-447. Double prism for totally reflecting refractometers. Google Patents. Motiv und Erläuterungen zum Entwurf eines Statutes der Carl Zeiss Stiftung. Vopelius. Rudolf P. Anamorphotisches Linsensystem. German Pat 99722. Gesammelte Abhandlungen. 5 volumes. Release from 1904 until 1940. New York, New York. Hildesheim. LCCN 94,235,187. Lammer, Otto. Riker, Fritz. Die Lehre von der Bildungsstehung im Mikroskop. Braunschweig, Germany. F. Weiganzone. LCCN 10,017,693. Sozialpolitische Schriften. Jena, Germany. Gustav Fischer. LCCN 49,036,118.